Hello and welcome again to my Physics Online video lecture series. Today's video we're going to be talking about Pascal's principle. This is a continuation of our discussion of fluid statics for an introductory physics course. So let's get right into Pascal's principle. I don't know if there's much to say in our little recall portion of the video. I guess that you should maybe recall that pressure was defined for us as a way of getting sort of like an averaged force over area. So this is sort of a way of averaging force on an object by basically taking total force and then dividing by the area over which that force is applied. So pressure is averaged force per area, or in other words, P is defined as F over A or S or whatever you want to use for your area. And this is a force that is being applied by a fluid, so it is applied by fluids. And again, what is a fluid? A fluid is basically states of matter that are not just solids. So it could be a liquid, it could be a gas, it could be a plasma. And I think that those two things being recalled is probably adequate for today's video. So what does Pascal's principle say? So Pascal's principle is named for Blaise Pascal, who was a French physicist and philosopher, and among other things contributed Pascal's principle in philosophy. He contributed what's called Pascal's wager, which you can read about in the Pensées. The Pascal's principle basically says that if I have a fluid, let's say that I have a fluid that's confined to a container like this, and maybe the fluid is present here, let's say. And we know that at this point right here, some depth h, the pressure from the fluid should be rho times g times h. I suppose that's something that we would also maybe recall. And then there's also some additional P naught out here from the atmosphere. Then this actual pressure is P rho gh plus P naught. And if we modify this by, let's say, putting an object that has to float on the fluid, or maybe it's not even floating, maybe it's more like a piston that can be pushed down on the fluid. So we have additional pressure. Maybe we could call that delta P that's being applied, or P applied, something like that. Let's call it PA for applied. Then the pressure at this depth will change to rho GH plus P naught if applicable, or P applied. Okay, so put differently, if extra pressure is applied to the fluid from outside of the fluid, then that amount of extra pressure is applied to all parts of the fluid. So we could say, in some sense, that Pascal's principle now could read P total is equal to P fluid plus P external. So that basically is your Pascal's principle in a nutshell. Now, the idea behind this is essentially that if you have some fluid and you start applying pressure to it, then the fluid has to basically apply pressure back, for example, to your piston or whatever. And that pressure back basically means more force, and that more force requires that fluid at a deeper depth also applies more force, and so on. So again, if I draw this schematically, You could think of this fluid as being maybe in like layers like this. So we've got, let's say, water. I have these water molecules here. I've got another layer of water molecules down here. And then I've got another layer of water molecules down here, and so on. So with no external forces or pressures being applied, essentially this layer of water molecules must hold up the two that are above it. So this layer right here has to support this layer as well as this layer, as well as anything that's on top of the two layers. In other words, each layer of your fluid is basically being supported by the layer below it, and each lower layer ultimately has to support all the layers which are above it. Okay, so in some sense that's part of why this whole pressure is equal to density times G times depth would work. On some scale, the greater your depth, the more layers that you're having to support by that deepest layer. Okay, now Pascal's principle in some sense actually relies on this, but in some sense predicts it. Let's take this same scenario. So let me go ahead and maybe like copy this stuff right here. Let's say now that I place something on top of all the fluids. Maybe it's like a piston. So here's a piston or a raft or something. And we're applying downwards some amount of force on this piston. It makes contact with the uppermost layer of the fluids, but it doesn't sink into the fluids. Well, force is being applied downward by this piston, and that means that the fluid right here has to apply an upward force that is equal to this downward force in magnitude, but opposite in direction. So F fluid in response to F piston. Well, in some sense, you could say, therefore, that this layer number one is now supporting the effective weight of this piston. And by effective weight, I mean not just the literal weight of the piston, but the actual force with which the piston is pushing downward on the fluid. And that means that layer number two has to also support the effective weight of the piston plus the first layer of fluid. Layer 3 has to now support the weights of fluid 2 and 1 and the effective weight of the piston. This means that we now have some additional force that each layer of the fluid is having to apply. And that in turn implies that each layer of the fluid has some additional pressure that it's applying. And that additional pressure is both upward and downward and left and right, and that will be equal to whatever this force from the piston is divided by whatever area the piston has. So that becomes your external force. So this piston is your external force. This fluid is basically the force that you get from this original diagram. And remember that this external pressure would be this force divided by area. So there are many applications to this, everything from hydraulic jacks to hydraulic brakes to any hydraulic system basically is just making use of Pascal's principle. So to illustrate it very simply, a hydraulic lift, what you usually have is a person who has like a little foot pedal, okay, and they like push on the pedal. Push down, push up, push down, push up. This pedal basically depresses a little piston that is connected to a small tube like this, filled with fluid, water for example. And then this little tube opens up into a much bigger tube like this. And the much bigger tube is connected to essentially a hydraulic system that has a lift like this in it. And the hydraulic system is such that when this is depressed, some force is applied downward onto all the fluid, and then you end up getting that same pressure applied upward here on the lift. And so you've got like your car sitting here on the lift like this, and the car, you know, weighs quite a bit more than the person does, weighs quite a bit, but the amount of force that's being applied upwards is the same pressure that the foot is applying times the area. So, you know, maybe you have a force of 50 newtons here, 50 newtons, and you've got some cross-section area right here. We could call this A1. This right here has cross-section area A2. And this ratio of forces, since the pressure's equal, P1 equals P2, this is Pascal's principle in action, that means that F1 over F2, or F2 over F1 more appropriately, F2 over F1, should look like A2 over A1. And so F2, this total force upward, and this total force downward, F1, F2 is A2 over A1 F1. So if this is a, let's say 600 kilogram car, 6,000 Newton car, I'm applying 50 newtons of force down here. I need 6,000 newtons worth of force up here. That means that this ratio F2 over F1 is, let's say, 6,000 newtons up. This would be 6,000 newtons over 50, which is 12. And that means that A2 is 12 times A1. So if this area right here is, let's say, 1 square centimeter, then the area of this piston over here has to be that times, whoops, I miscalculated though, this should be 120, not 12. This should be 120 square centimeters. So if A1 equals 1 centimeter squared, A2 is 120 centimeters squared. Now 120 centimeters squared is still not all that large. You know, divide by 3, you've got 40. You're looking at a circle that is about, let's say, 6 3/4 centimeters in radius. Okay, so that is a little bit wider than my hand. You know, maybe a little narrower than from pinky to thumb is how big around the shaft needs to be to lift this car. So in actuality, your hydraulic system usually has like a shaft like this, and then there's like the actual platform that's being supported by the shaft. And then the platform is what the car is sitting on. So this right here is what's actually submerged into the fluid. And then this right here is the lift that the car is on. In any case, that's a basic introduction to Pascal's principle, and that is an application thereof. So that's all for today's video. Hopefully you learned something, and thanks for watching.